Hello everybody. I'm very honored to receive the ACP Doctoral Research Award. I really regret not being able to attend the event in person, but I hope you'll enjoy my talk today nonetheless. I'll be discussing a few results I've particularly enjoyed working on over the last few years. All of these are on the topic of approximation of constraint satisfaction problems. To this end, let's fix some notation on constraint satisfaction problems. Consider some relation R. Then we define CSP of R as being the constraint satisfaction problem where every constraint is of the form some tuple of variables belongs to the relation R. For example, let not equal C be the binary disequality relation on domain 1 up to C. Then not equal C is precisely graph C coloring. Why is this the case? Well, in this problem we have a set of variables and a set of constraints. Each constraint imposes a binary disequality between variables that must take values between 1 and C. This is exactly the same thing as graph C coloring, where edges correspond to constraints. Another well-known CSP is 1 in 3 SAT, or rather monotone 1 in 3 SAT. We can model this as a fixed template CSP in the following way. Let 1 in 3 be the relation admitting 3 tuples, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then CSP of 1 in 3 is monotone 1 in 3 SAT. In this problem, you're given a set of clauses, each containing exactly 3 variables, none of which are negated, and the goal is to assign 0 or 1 to the variables so that in each clause, exactly one variable is set to 1 and the other 2 are set to 0. In order to discuss qualitative approximations of CSPs, I also need to introduce the so-called promise CSP. The general pattern in this problem is fix R and Q, two relations, with R being a subset of Q. Then PCSP of RQ says, given a yes instance of CSP of R, solve it as a instance of CSP of Q. Since R is a subset of Q, this amounts to relaxing the output requirement of CSP of R to CSP of Q. For example, let's fix C less than or equal to Q. Then PCSP of not equal C, comma, not equal Q is approximate graph coloring. Given a C colorable graph, in other words, a yes instance of CSP of not equal C, our goal is to find a Q coloring. In other words, a solution to the instance if we interpret it as an instance of CSP of not equal Q. This problem has been worked on a huge amount. It's a central problem in theoretical computer science. Just to sample some of the most recent results, on the positive side, there's recently been some very exciting progress. Using semi-definite programming and combinatorics, given a 3-colorable graph, one can find an O of n to the 0.19539 coloring in polynomial time. On the other hand, for hardness, given a 3-colorable graph, it turns out to be NP hard to find a 5 coloring. If you think about it, the gap between these two results is really large. We know that 5 is hard, but O of n to the 0.19539 is easy. But for example, we know nothing about 6 or 7 or even log n. At least not unconditionally, that is. It is, however, conjectured that 3 versus O of 1 coloring is NP hard. How would one even go about proving this, though? Perhaps studying a different promise, other than 3 coloring I mean, might help us understand qualitative approximation as a whole better. It might open the doors from some new ideas for approximate graph coloring, but also might lead to some interesting problems all on its own. In particular, let's try approximating monotone 1 in 3 SAT. The first question is, however, what can we even consider to be a good qualitative approximation of 1 in 3? What could serve as an appropriate relaxation? If you think about it, 1 in 3 is defined, basically, by choosing a single coordinate of the 3 in each constraint. A natural generalization that follows this idea, at least the one I'll be going with for now, is linearly ordered coloring. We define LOK to be the relation that admits a triple xyz of values from 0 up to k minus 1 if and only if that tuple has a unique maximum element. In other words, the maximum value appears exactly once. The corresponding constraint satisfaction problem is called linearly ordered K-coloring. As our first example, LO2 is identical to 1 and 3. Why? Well, if the maximum in a tuple were 0, then all three elements in the tuple would have to be identically 0, and thus the maximum would appear 3 times, not once. So, in any tuple admitted by the relation, the maximum must be 1. And if 1 appears exactly once, the remaining 2 elements must be 0. So we get 1 and 3. If we go now to the next size step up, LO3 contains the tuples 1, 0, 0, 2, 0, 0, 2, 1, 1, and 2, 1, 0, plus all symmetric permutations of them. Why is this the case? If the maximum is 1, as before, we get 1 and 3, basically. If the maximum is 2, then we must have exactly 1, 2, and then 2 values strictly less than it. So 2, 0, 0, 2, 1, 1, 2, 1, 0, and all their permutations. It would not be valid, for example, to allow the tuple 2, 1, 2 or 1, 0, 1. So let's consider approximate LO coloring, approximate linearly ordered coloring, as a good qualitative approximation version of 1 and 3 SAT. It was conjectured by Barto Battistelli-Berg that for any constant k and l, PCSP of LOK versus LOL is NP-hard. Spelled out, given an instance of LO coloring that's satisfiable, that is, a set of triples where I can assign a color from 1 up to k, from 0 up to k minus 1 to every variable, such that every triple has a unique maximum, it turns out to be NP-hard to find such an assignment using L colors for constant L, no matter how large L is relative to k. So, what's the current state of the art on this problem? First, on the tractability side, we managed to prove that given an LO2 colorable instance, you can even find an LO log n coloring. This is in contrast to the approximate graph coloring case, where the best known algorithms give something basically in the polynomial regime, n to the some power. Via some sparsification ideas, we managed then to prove that you can even improve this, albeit slightly, to 0.999 times log base 2 of n. That's exactly 3 nines, it's not 999 repeating. To be honest with you, I find the ideas behind this sparsification result more interesting than the fact that you can reduce the number of colors by this small amount. But this is going to be something I'm going to get into a bit later anyway. It was also proved by Krokin and Vagnozzi that given an LO2 colorable instance, it's NP-hard to find an LO3 coloring. And finally, at LIX this year, we managed to prove that, conditional on the rich 2-to-1 conjecture, which is a variant of the unique games conjecture, the conjecture turns out to be true for k at least 3. In other words, given an LO3 colorable given an LO3 colorable instance, it's NP-hard to find an LOL coloring for any L, fixed of course. In this talk, I'm going to discuss the 2 algorithms I mentioned above, together with a short discussion on the last hardness proof. The key fact that we'll be exploiting over and over again today is that LO2, in other words 1 and 3, is linear. Fixing one thing to be 1 and 2 things to be 0 is the same as setting x plus y plus z equals 1 over 0 and 1. This is a key observation, even if it's a bit simple, and in some sense, it's what makes this problem easier to approximate than 3 coloring. Not equal 3 cannot actually be written in this way. So, let's describe the LO2 versus log n approximation algorithm. First, let's relax our system of equations. Instead of saying x plus y plus z must equal 1 exactly, let's allow x plus y plus z to just be congruent to 1 mod 2. So, suppose you write down one of these equations and find some solution. And let S be the set of variables set to 0 in this solution. Then, S must intersect every constraint in an even number of positions. Why? The allowed assignments are 1, 0, 0, in which case we intersect twice, or 1, 1, 1, in which case we intersect 0 times. So we can set S to be the minimum color in our entire solution, remove all constraints incident to S, and continue coloring what remains recursively, using only bigger colors, so as to enforce that S is set to the minimum color. Let's think why this should work. Well, a constraint that's intersected in 0 places is solved correctly, recursively of course. We haven't done anything for it in this step. More interesting is the case where we have a constraint intersected in 2 places. Since we've set S to be the globally minimum color and colored all things outside of S with strictly larger things, then any constraint intersected in 2 places by S is colored correctly, since there is a unique maximum, namely the unique variable that does not belong to S. So such constraints are also satisfied. Let's consider some example. Look at this instance where every triangle represents a constraint. We can find some set of variables that intersects every constraint at an even number of positions. Let's consider, for example, these blue variables. If you look at it, every triangle intersects only an even number of blue circles. If we set these blue variables to a very small color, and then set everything else to something bigger, then every constraint is either satisfied immediately, these are these grayed out constraints, or will be satisfied recursively in a future step. This is this still not grayed out constraint. So our goal, therefore, is to find a solution to this system of relaxed equations that sets as many variables as possible to 0. That's so that we color as many things as possible at each step. How can we do this? Intuitively, you should think that a random solution to the system of equations should set about half of the variables to 0. Because you know, it's either 0 or it's 1. Half of the time it's 0, half of the time it's 1. Does this actually work? There's a slight problem with this, unfortunately. If you consider the following system of equations, for example. At first glance, this might look a bit undecipherable, but if you look at the first 2 equations specifically, they imply that A and B are congruent to each other. Then, if you look at all the further equations, keeping in mind that A and B are congruent to each other, it follows that X, Y, Z, and so on are all forced to be 1. So in this instance, a random solution has mostly 1s. The only variables not forced to be 1s are A, B, P, and Q, a negligible fraction of the total. The problem with this instance is that certain variables are forced to have a fixed value in every possible solution. But if you think about it, those variables are very constrained. They should be easy to deal with. In fact, if a variable has a single possible value in the relaxed system of equations, a fortiori, it must have only a single allowed value in the more constrained original system of equations. So, what can we do? We can just fix those variables to begin with from the start, remove them from our instance by a bit of propagation, and keep on going. So, with this in mind, we can assume that we have no fixed variables at all, and therefore a random solution does in fact set about half of the variables to 0. Therefore, the procedure explained earlier, where we continuously color with higher and higher colors, does in fact work, and does in fact use roughly log n colors. You can lower this by a constant additive difference, even by a log-log factor, but this log-log additive difference isn't that important. This gives us the advertised LO2 versus LO log n coloring in polynomial time. Let's consider a quick example. We can look at this instance and inspect it to see if any variables must be fixed to a certain value in all mod 2 solutions. It turns out, if you look at it enough, the variable at the very right must be 1. And by a bit of simple propagation, its neighbors must be 0. So we get to this. We now fix these variables once and for all, and we go on to solve what remains. If we find a random solution to the mod 2 equations we discussed earlier, you can get something like this, for example. We can color this with the next color, 2 in our case, and keep on coloring recursively. And what remains is really a trivial instance, so we can color everything with a single color. We end up, therefore, with an LO4 coloring. Well, that's all well and good. And notice that, as opposed to the polynomial regime that one gets for graph coloring, for this problem, you get the logarithmic regime. However, it turns out that we can get a slight improvement to this algorithm, and on the way, get an interesting generic sparsification idea that can work for any qualitative approximation problem of 1 in 3 SAT. Let's use the following rather simple idea. If two variables, x and y, are forced to be equal in every single solution, just merge them. Suppose that we apply some merging heuristics of this type, get some sparser instance, solve that instance, and then unmerge the variables. Maybe we get lucky and need fewer colors at the end. This might be able to improve our algorithm's performance, but one question you might have is, why merge variables rather than just delete irrelevant constraints? That's also a perfectly valid thing to do, no? Well, it turns out that deleting constraints is a bit less obvious to do for qualitative approximation. Consider, for example, 3 versus 4 coloring of the following graph. Let's look at this graph on the top left. The two vertices on the bottom right of this graph must have 2 different colors, since they have an edge between them. And therefore, the 2 vertices on top, both of which are neighbors of both of the 2 vertices mentioned before, must have the same color in every 3 coloring. Why? Both of them have only 1 color left to choose from the original 3 colors. That means that the 2 edges from these 2 vertices to the vertex on the bottom left are redundant. One of them is never needed. But if we remove one of these edges, we can accidentally introduce a new 4 coloring that wasn't valid before. Those constraints were irrelevant to the 3 coloring, but they're not absolutely irrelevant to all possible qualitative approximations, in particular for 4 colorings. This shows why removing constraints isn't easily compatible with qualitative approximation. Conversely, merging just works out of the box. In the same situation, the exact same reasoning shows that the top 2 vertices are always colored the same, so we can just merge them, find any 4 coloring, and then unmerge at the end. So let's introduce some merging heuristics. Let's consider the following heuristic first. If 2 variables, x and y, are implied to be equal by the mod 2 relaxed system of equations, then we can identify them. This turns out to be very easy to check via linear equations. Turn every constraint 1 in 3 of x, y, z into x plus y plus z equals 1 mod 2. Try to solve the system but setting x equals 1, y equals 0, or vice versa. And if both of these assignments turn out to be impossible, then merge x with y. This is a valid heuristic because if 2 things are equal in the more relaxed system of mod 2 equations, they must be equal in the original, more constrained system. Heuristic 2 is a bit stronger in that it uses a bit more of the structure of the problem. If we fix a variable x to be 1, then all of its neighbors, meaning variables sharing at least one constraint with it, are forced to be 0. So, fix some variable x equals 1, propagate 0 to all of its neighbors, then, for every other variable z, check if setting z equals 0 is consistent with the mod 2 relaxation and all of the choices we made so far. If it's not consistent, then x equals y implies z equals 1. In other words, x is less than or equal to z in every single solution. If we deduce this between x and z, let's write down this curly less than between x and z. Heuristic 2 says the following. If we have a cycle in these implications, then we can safely merge all of the variables in the cycle. So, let's recall. Heuristic 1 says, merge things implied to be equal by the mod 2 system of equations. Heuristic 2 says, if there's any cycle of implications, merge those variables. These might seem like fairly innocent heuristics. You might not expect them to do anything particularly interesting. But it turns out that any instance where heuristic 1 and 2 have been exhaustively applied has at most O of n to the 1.9972 constraints, just a bit less than quadratic. This is important because if you apply the earlier algorithm with a bit more analysis, you can prove that this slightly reduces the number of colors you need. This yields the advertised LO2 versus 0.999 log n of coloring that we mentioned earlier. But to me, again, more importantly, these 1 and 3 sat sparsification techniques can be applied to any qualitative approximation of 1 and 3 sat you're interested in. Now, how do you prove this? Magic? Well, no. With additive combinatorics. This result, to me surprisingly, follows from the polynomial Freeman-Ruja theorem that was very recently proved in 2025. So apparently, even such deep results in additive combinatorics and number theory, like this polynomial Freeman-Ruja theorem, have applications to simple problems like approximating 1 and 3 sat. Finally, let's discuss the hardness result we recently proved. PCSP of LOK LOL is NP hard for 3 less than or equal to k less than or equal to L, assuming the rich 2-to-1 conjecture. How can we prove this? It turns out that we have a really big hammer for showing this kind of a hardness result. If the promise R is symmetric and reconfigurable, and I'll get to what reconfigurable means in a second, and Q has no constant tuple, then PCSP of R, Q is NP hard, again assuming this rich 2-to-1 conjecture. What do we mean by reconfigurable? Well, it's quite simple really. For any tuples of R, let's say x and y, I can go from x to y, changing only one coordinate at a time in every tuple, and always staying within the relation. I'll get to an example of this later if it's not completely clear. So, with this theorem in hand, it would be sufficient for a hardness result to prove that LO3 is reconfigurable. And it turns out it is. To observe this, we just need to construct this reconfiguration graph in which every vertex of the graph is a tuple of LO3, and I've put an edge between two tuples if and only if they differ in exactly one coordinate, or equivalently have Hamming distance 1. Reconfigurability of LO3 then amounts to this graph being connected. You can see, in fact, all of the tuples of LO3 in this diagram. For example, all of the 1, 0, 0 tuples are on the corners and so on. I really personally found this picture very pretty, but somehow all of these reconfiguration graphs turn out to be nicely symmetrical. To conclude, qualitative approximation of CSP, in particular PCSPs and this LO coloring problem that we talked about today, have both really interesting approximation algorithms touching on unexpected areas in mathematics like additive combinatorics and so on, and also some rather strong and unexpected hardness results using the quote-unquote topology of reconfiguration spaces. In any case, that's more or less everything I wanted to say. I hope you enjoyed the talk. I hope you enjoyed the results. I really hope you have a good time for the rest of the ACP. Thank you for your attention. Quote-unquote topology of reconfiguration spaces. In any case, that's more or less everything I wanted to say. I hope you enjoyed the talk. I hope you enjoyed the results. I really hope you have a good time for the rest of the ACP. Thank you for your attention.